During the weekends when you're not so busy with your schedule and you have time to laze around or enjoy the day outside, maybe take a jog or probably read a book outside in the park, what the sunlight alarm clock does is that it wakes you up if it is a good day outside, and it lets you sleep by not ringing the alarm if it's not a good day outside. So the basic agenda of this project is to use the light sensor, that is the PDV P9003, to sense the light intensity, and the moisture sensor and the temperature sensor to sense the temperature and moisture outside, the humidity basically.
To go about this concept, we first decided to use the light sensor to sense the light intensity over a number of days when the weather varies from sunny to cloudy and rainy. The light sensor was placed outside of the window to record the light intensity data over a period of 3 hours every morning. The humidity sensor supplies the confidence level in deciding whether it's a good or bad day.
This is the processor tree of our project. As you can see, these are the three sensors that we have included in our project: the light sensor, the temperature sensor, and the humidity sensor. The three sensors are connected to the DAC, and the DAC will collect signals from the three sensors. After that, the DAC is connected to the LabVIEW on a laptop. We'll get three charts of our three different sensors at the first place, and then we have to add in some indicators and transfer functions so that we can translate the complicated responses to understandable information. Finally, when the three informations matches the condition that we have set up previously, the trigger will turn on, which means the alarm clock will ring.
The light sensor, we are using a photoresistive sensor. A photoresistive sensor is a sensor in which the resistance decreases as more and more light is exposed to the sensor. There's a semiconductor within the sensor which allows electrons to move more freely as the sensor is exposed to light. As the electrons move more freely, the current ultimately will increase. We all remember Ohm's law. Voltage is equal to current times resistance. So as the sensor is exposed to more light and the electrons are able to move more freely, the current will increase, and as we keep the voltage constant, that means the resistance will thereby decrease.
Use the PDV P9003 Firefly light intensity sensor. This sensor is made up of photoconductive photocells designed to sense light from 400 to 700 nanometers. Its operating environment is -25 to 75 degrees Celsius. This wide range of temperature allows for our alarm clock to function properly in a diverse set of environments.
Yeah, so the temperature sensor. The temperature sensor that we plan to use is the LM90422. It is basically a silicon PN junction sensor, and current is forced through the junction. And as the current is forced through, the voltage changes, and the voltage change is directly proportional to the temperature, and that is how we measure the temperature.
The humidity sensor is a capacitance-based sensor. It is made out of a ceramic or polymer material, and the capacitance changes as the polymer or ceramic material absorbs more and more water.
Our humidity sensor uses a ceramic material sandwiched between two electrodes, which form the capacitor. The voltage is directly related to the current and inversely proportional to the capacitance. The ceramic material absorbs the water, which increases the capacitance. This results in a decrease in voltage. The amount of absorption is dependent on the relative humidity. This is the ratio of actual vapor density to saturated vapor density. Our sensor has a 2% relative humidity error and is calibrated for 3.3 volts and 5 volts.
Let's take a clear look at our connections. As we can see, this is our sensor that we use in our project, and some of the wires are connected to the ground, which is plugged in the breadboard, and some of the wires are plugged in the jack. We can see there is analog input and analog outputs. Finally, the signals are sent to the laptop, and it opens the response in the lab view, which we can do some data analysis works.
The DAQ assistant acquires data from two sensors. Here we split the signal. The light signal flows to the upper part, and the temperature signal flows to the lower part. Here we use the moving average filter to eliminate the disturbance to the light sensor. Here we set a limit of the light intensity based on several experiments we did on sunny, cloudy, and rainy days. Since we are using the moving average filter, the first 10 seconds signal cannot reflect the true value of the light intensity, so we use the elapsed time function to cut these fake signals. Now let's look at the temperature part. We are interested to know the temperature outside, so we use this formula function to convert the voltage to temperature. This formula is derived from the specification sheet of temperature sensor and then revised by us based on several experiments. This part is used to avoid extreme weather condition. If the temperature is too high or too low, this alarm will not ring even if it's a sunny day. This is the time control part of our system. This ensures our alarm will only work from 6 to 10 o'clock in the morning.
Before I start the demo, I should explain that we will set the voltage of 1.8 volts so that the alarm will be activated in this room. So we run the system. In the front panel, we can see the current time and the current room temperature. When the current time lies between these intervals, the alarm is working. In this graph, we can see the value of instant light signal. Right now, because I'm blocking the light sensor, so the value is about 1.8. When I'm moving my hands, you can see the fluctuation in this chart, but in the average light waveform chart, you can see little fluctuation. And when the fluctuation happens, the alarm doesn't ring. That's because we use the moving average filter. Next, I will show how the alarm will ring. This time, I will move my hands for a long time, and the value is below 1.8. So this time, the alarm rings.
The main challenge that we encounter comes with the use of our product. Ultimately, we realize that the product cannot be placed in a position in which there is a lot of shade. What we want to accomplish with this product is to test how much light is around the area and ultimately wake up the user with an alarm actuation. So we understand the challenge to be placing the sensor in an area in which there isn't too many trees around to block light coming into the sensor.
So let me explain why our humidity sensor doesn't work. Our first attempt is the digital sensor. We met the difficulty that without the suitable tools, we can't interpret the data. So our second attempt is the analog sensor. This time the sensor is too small. We had to solder it into the circuit, but we still find it hard to decode from the responses.
The actual application, the actual usage of the sensor system that we have developed might sound a bit impractical to use during day-to-day life, and based on the limitations it has, that it can be used only in the summer and only during the morning time, and the sensor has to be facing the east, and considering all the obstructions that you might face when you're placing it outside, it might even turn out to be a bit more expensive. So Further development that can be done to this project is that we can use a sensor system for an apartment building, which the sensor system would consist of a number of light sensors around the building placed on the roof of the building, and the apartments, individual apartments inside the building could have a personal alarm which would go off based on the sensor data that is received from the top of the building. So that would actually add to the value of the apartment.